Okay. And what we're looking at here. That's pretty much it. Okay, this is another video on what we do while in lockdown. This one's load paths. Everything that's part of your house, whether it's part of the house or just sitting in the house, has weight to it. And you have to get that weight sitting on something, so it doesn't float off into space or whatever. Anyway, there's a rule: you want to have the shortest and straightest load path you can in engineering, particularly in airplanes. When you're building airplanes, the load path is everything. But in houses, we know we're gonna put the pads in the ground and put columns on it, or we're gonna put a footer down, which is just a wide part of the wall that's underground, and we build the house on that. So all the loads have to end up sitting on either a footer, which was what most of the world uses, or in the Philippines we use underground pilasters, piers. Now there's some things you don't want to do and things you do want to do. On the right side of this picture over here, you see an intersection. You have a top tie beam. This could also be the tie beams in the ground, but I was thinking top tie beam here. You have a tie beam, and then you have a beam coming in at an angle. Both those are sitting over this post. And so any weight that you transfer at that contact point has to go down the post. Now here we have a column going up to something else. Now it may be offset because you need a wider space here for a hall. Like you have to have a minimum about a 40-inch, a little bit more than a meter hallway in the Philippines. Less than that doesn't pass fire code. So you may have offset this and the wall, and this may be built into a wall. Now it may be the same thickness as the rendered wall and be invisible, but this is not good construction practice. You want to avoid that. There's some other things we're going to try to avoid. Let's take a look at some of them. In fact, let's make this bigger. I'm having to look around the phone. Can't see my... Okay, this is not the scale. I just hacked out a house real quick. It's a total of about 15 minutes to draw a frame. There are no specific dimensions in this. It wasn't designed for anybody. And this one is not a critique of somebody's design and suggested changes. In a way it is, because it's got some changes that were suggested to other people's builds, when they ask. If you ask and I can access my YouTube, I'll give you an opinion. Now, there are two houses in YouTube where they showed the construction, and one of them that is the completed house is a tour, where they did this. This is a concrete beam sitting outside of the footers, connected to a tie beam. And the one example, this is pretty much taken from their video, and the other one, instead of being short like this beam cantilevers out about 8 feet. And the beams are really tall. They're like 3 feet tall. But this one I'm thinking of, this is pretty much a picture of, this only sticks out about 18 inches. So it's not a lot of load, except that they put the wall. They've moved this wall out here. So now you got the weight of the wall, and the roof is sitting on the upper tie beam of up here. So all the weight of that side of the roof is going to be transferred into this. This is trying to twist this beam. It's not anchored. So let's see what we do about that. We're going to move this over here and move that down. And there's the same house. So here we see this. These things were drawn up like evenly spaced, and so they didn't land on anything. But suppose we changed it. Take. We're going to move something. And because I did this ahead of time, it's all connected together. It's a group. It all moved together. We're going to take and we're going to move this down a little bit. Okay, what we got now, we've got the two ends lined up with columns, and they can be tied right into the columns. And you really haven't lost anything here, because this is a balcony for a master bedroom. Rather than having that odd little corner that's in the actual house, your balcony now goes the width of the room, and the master bathroom. Well, it's full width too. So you have the tub and the shower, and you'd have a little bit of a partition wall out here. This one could be moved over there, and this one's centered up on here. There's some other improvements you would make. I would get one more tied into this, any way you want to do it. But if you took these two here and moved them down some, I would hook it into that. Anyway, that's a critique of that. Now, the next thing is, you have this is a multi-story house. And it's designed with a vaulted ceiling here, you know, a round top or an angle top ceiling with triangular windows on the end. But I was thinking, when I was sketching this up, I was going to draw a round roof up here, you know, and then side panels with whatever. If you put all these walls up here, you have to have something underneath holding them up. And the problem is that this house is drawn up with a, it's got a post here, but that's in the living room. And this upstairs room, it's sort of like a living area. It could be a giant bedroom, but it's designed to be a big open space. If this had a post here and all connected, or walls up here, then you need this post down here. But the way it is now, with no wall up here, this is an open area at the top. This bottom area, you can design this shorter of the two beams to be really load bearing, and do away with that column, and the footer and everything goes along with it. The example here of let's look at this a second. This is taken from a problem I had back in the 70s. I was putting a conveyor in an industrial building, and they always told us, you know, engineering, pull the original drawings, or have the girl down there in the Xerox room, she'll pull them, you're not allowed to touch them, and have her burn you some prints. And they were done as blueprints back in the day. Well, this was a steel mill, and it was put up during the Second World War. So a lot of the stuff was put up different than the prints, and the prints were never changed because it was wartime. And they were on to the next project. Yeah, you got that done? Good. We'll go over and do this for a while. So you had columns that weren't sitting on top of the columns down below it. This column was on the third level up. That's 60 feet off the ground. And then there's 3 more levels above this column. What this column was sitting on wasn't even on this beam. It was over here someplace. And there was a half-inch steel plate floor. This column was welded to the floor. There was absolutely nothing underneath of it. But over here, about 8 feet away, there was a fabricated column. It was 4 feet tall and 22 inches wide, and had a doorway cut out of it. Another story. They cut doorways for catwalks down through the building, through the columns. I wanted to put a 2-inch pipe with a hole saw. I wanted to put a hydraulic line up in the corner near the door. I couldn't get permission to put a hole in that because it was a structural column. But 8 inches below the top of that rounded door, they cut the whole column out. Anyway, I go up there and I look, and I'm up by Maynard Ferguson's office, and everything looks great. And then I got to thinking that what the older fellow told me. He says, make sure that it matches the drawings. So there was like a little hole here in the floor, like a bolt is missing or a rivet, or somebody just drilled a hole. I don't know what it was. It might have been when they were doing construction, they put something in there to pick a plate up with, and then just took the lifting piece off when they were done. I take a string, tied my pencil on it, loaded through the hole. Okay, what my idea was to go down and because I couldn't see down through the floor what was down there. I went down, I looked and looked and looked, could not find my string. I said, look, some fool up there saw me put that string to the floor, and he's pulled it up and laid it on the floor. This is a joke. I went back up there, string was there. I says, well, where are you? I know you saw me coming back up here and you put it back, but I couldn't find anybody. I backed down, no string. Back up, string still through the floor. Back down, I says, I'm looking around. I back up and I feel something behind me. I was 10 feet out into the middle of a floor, and there was my string that was right by the corner of this column. But rather than this being sitting on this or really close to this 4-foot wide column, it was out dead in the middle of a floor. And there was a couple pieces of 8-inch channel going near it, and that was it. So you have a concrete house, and you can find it, your load path, which should be straight down this column and then across through here, through your floor, and down through this to your stuff in the ground. They may not line up. They may have been built with this in the wrong place. Now, most Philippine construction, just the way they do it, that's kind of hard to do because they run the rebar straight up to full length of the rebar if they're going to be a second floor, or even if they're just going to put a concrete suspended slab up there. You run them up and then you bend them over into the floor slab. But if you've bent them into the floor slab and then decided to add something additional on the house, then you got no rebar sticking up out of the slab to show you exactly where that column is down there. And somebody can measure left instead of right. You know, they're looking at it from this side on the back, and they say, okay, it's 18 inches over. So they get up and they turn around, and now they're putting it over here someplace. When they were measuring from something, they should have put it here. They've measured basically the wrong direction. And that's pretty easy to do, actually. Anyway, you want to avoid that. Well, back to load paths. You can see the concrete, reinforced concrete frame. You have these joints, you can call them knuckles, you can call them whatever you want to call them. But they collect up all the loads to the ends or whatever, and then they transmit them down through other beams and the floor slabs and another floor slab and a subterranean column into a concrete pad down. That's your load path, straight down. These beams here, they're sitting on the columns, so they have to transfer all of their weights that you put on them to the end points and send that down the columns. So you calculate the rebar in these beams for how much the middle of the beam would be trying to be bent. What's my time here? I make too long of videos. I don't see it. I know there's a clock, but I can't see it. Or maybe I'm not recording. That could be it. Never can tell. Okay, we'll just guess. Still not too long, maybe. So the beams are calculated for the part which will be in tension under gravity. Earthquakes can be hopping up and down, so you need to put some bars on the top as well. But this is going to be the weight of your floor slab. Well, this floor slab for sure here. And this might be HardieFlex or something. That's the only load on that. And then your roof load would be on it. Now, if this was the upper floor and you had a built-up angle iron roof trusses, big triangles basically, and cross brace and brace down here and a four-sided roof, and and all kinds of intricate angle iron and joints. You say, oh, it's just sitting on top of this. And that's not altogether true. The roof tin is bolted to the outermost pieces of these angle irons. They're sitting on a roof that's in the sun. So the temperature difference in the peak of a roof compared to down here, it can be 20 degrees. So this top piece of this triangle is longer in the sun. And because of the way it's tied here, tied to the middle and tied back, it tries to make this side longer. So it's putting a lot more weight on this than what you think it would. So you can't put a 4-inch column up here and hide it in a wall if this is a 60-foot span. You know, you have to size things pretty much according to what you're doing. This is about a simple house, isn't it? I don't think there's much else to talk about on this. Oh, there's one thing to talk about. You're thinking about your house, you're thinking about it upside down. The way this actually works, and the way it was done at Villa Cecilia, is we figure out all the weight that's going to be at a certain level, like the roof, down to where the roof meets the rest of the building, and you add all that up. Easy to do in CAD because you have the lengths of the parts, or you have it drawn 3D, and you know that steel is 480 pounds at a cubic foot in English terms. You know exactly how much it weighed. And you know that 0.6 millimeter roofing weighs so much a square foot, and you put all that in it, and you throw something in there for the conduit and wires and stuff you can have hanging off the roof. And that goes down onto this this upper tie beam. And then the anything that's hung off the bottom of these beams, like ceilings and stuff, that weight goes to calculating these beams and these tie beams are added into it. And that tells you how much you're going to resist, how much load you've got on each of these columns. And then you can come up with a square footage of your columns. If you say your concrete's going to be strained to 2,200 or 2,500 pounds a square inch, and you divide all that weight, you'll find they're not very heavily loaded. So they're generally oversized on this upper level. Our upper level beams are 22 by 28, I think. So then you get down here and you add the weight of these columns. You got all the weight you had up there, plus the weight of the columns, plus the weight of the floor slab, which is considerable, especially in our case because it's sort of circular and it's 8 inches thick on the inside, and the outside edges are 6 inches thick. That's because it's actually roof all the way around the house, and we want water drainage. So you add that floor slab and these columns to that weight, and that tells you what this column down here has to hold. And those are 29 or 30 by 35. They're bigger. The thing is that these are not carrying as much weight as these, so no use taking up floor space more than you have to. So this column is bigger. Now, because of the way we built the house, this column and that column are one continuous pour. Oh, golly. Go back. There you go. That's the nice thing about CAD. You can drag this stuff out of the way if you can't see what you're doing. And down here in the ground, we weren't sure what the soil bearing was. There's an absolute code minimum of 4 feet by 4 feet. I don't care if you're building a chicken shed. That's the minimum. Houses are generally done a little bit bigger than that, like 5 feet U.S. Because this was a 2-story house and we only had 20 columns, this has 16. And this house is nearly as big as ours, but it has 16 columns. And that has to be carried by these pads down here. And so they carry so much to the unit of area, and we decided to make them 6 feet by 6, actually 2 meters by 2 meters. And then because the holes weren't exact, we dug them with a backhoe, and we marked out the holes for the backhoe with Coat Saver paint and a 3-inch wide brush on grass. so you can guess how accurate that was. So some of these holes are 8 inches out of place. And so what we did is we found the centers actually when we actually had something to hang a string across, and we made the holes, particularly at the bottom, so they were centered on the columns. And some of these are 7 feet by 6. And some of them are 7 feet by 8. But the question is you column in the center of it. If you put it on the edge, you can tilt. Your load path isn't on the center of the piece that you're carrying the load on, so it tends to turn it upside down. And then our columns, we didn't do any disturbed land, so we found the deepest one with a transit and the shallowest one with a transit, and figured out how much concrete difference there was. And we just poured concrete with no rebar, just like putting in gravel. It had an advantage over gravel in it. Water wouldn't be all down in the bottom. We could get rid of the water above the concrete, we scoop it out, and it didn't go in the ground. So when we put these big heavy columns on here, it didn't just push them in the ground. But anyway, every connection in your house is a load path. This beam here, its load, and all of the loads, it collects up along the length with everything that's sitting on it or hung from it. They go to a point, and all those things, you have to add all those weights up, and they need to go straight down to your foundation. You don't want to have any offsets. We have no offsets, but what we do have is up on the upper floor, these beams here compared to those beams, these beams are 12 feet longer. This going out here, and there's a floor slab underneath of them, and the slab below that slab goes down to this level here. That slab is that big, so we have posts out here, and these outer posts are out past where the end of these the beams up here are. They end over here someplace, and then it's another 8 feet out to that outer post. But what we've got is we poured concrete walls. So we have a tie beam that goes from this post to the one out there that's in the living quarters level. So we have something we can set weight on. And this is all poured concrete. It's like one continuous column from here to there. Or a beam that's 10 feet, 1 and 5/32 tall. Plus it got the floor on it. So that weight out here is carried on this poured concrete wall. Even though there's not a column here, it's just like having a 10-foot tall beam. It doesn't deflect. There's never going to be a problem with that. And up here at the top, this beam is, if you didn't have the wall, would be cantilevered. Half of the weight of it here and there is balanced over that. So it's really not carrying the weight of the beam so much out here as you'd think it would, because if this wall was 12 feet on the other side is just balanced on it. That's like this beam and that beam. Half of the weight of this beam, half the weight of that beam is sitting on this. So our load path up here, we take all that out of effect, and then we end up with a 24 foot, no, it's more than that. It's almost 30 foot round hole in the middle of the house. It's got no columns underneath of it. So this beams go clear to the other side, and they have a round hub in the middle because that's a circular shape. But a lot of our weight is counterbalanced. And if you wanted to build a roof deck out here, I don't care if you're making a carport or you just want something to sit on with a chair, and you don't want a bunch of things in the way to block the view, you can put a concrete slab out here. You have to calculate the strain in the top of the slab because it's going to be carried on these whatever columns you get back to. And then behind that, you have to have probably a third the width of the parts is hung over. If it was a third the width and three times the thickness, like if this was a 6-inch concrete slab, this piece over here would be 18 inches. And at that point, the weight is balanced on this here, on this thing that is sitting. It's like an axle. So anything that is more than that will tend to press the back end down. Frank Lloyd Wright built a place called Falling Water. You can look it up on the internet. It's got cantilever decks everywhere. But the quality of the sand on his site, that he built everything with materials from site except the Portland cement. And he built a lot of stuff out of ledger stone. That's where ledger stone got popular, is with Falling Waters. He built ledger stone on a lot of things, but that was the first major building that had it. They had some cracks up here because, like our helical stairs, if you've seen any of our videos, the handrail part is like a wall up from the stair treads, and it's sort of like a handrail thing down, the stair tread, and the handrail thing up, like a big curved wall. That U-shaped trough it's got a bunch of rebar in it. And that's why it doesn't have to have any supports anywhere. It just hangs from the floor up above, and it's sitting on the bottom floor. There's a couple pins there to keep it from sliding around in an earthquake, but it basically hangs from the top. And it's that shape of that. And plus the floor up there is one continuous casting with it. It was all poured at the same time. But Falling Waters, they have big fireplace chimneys and stuff in the house. And there's a fireplace and a flue, but the rest of it is a solid chunk of masonry and rebar that goes up and ties to these cantilevered slabs. It's a really nice engineering job on that thing. He did a lot of things with big open spaces, Frank Lloyd Wright. I've always liked his work. He's way better than the rest of us. I think you have to have SketchUp Pro from Google if you want to do 3D like this. Anyway, beware of load paths that are trying to twist something rather than press down on something, like this cantilevered piece out here, which was, I'm not going to put it back. It irritates me to have it over, have it sitting like that. We're going to leave it like where it sits. Anyway, this drawing is a piece of junk. How do we got up here? Oh, is that all? No, there's something up there. Oh. Okay, wait a minute. Expand the topic. Whole page. There must be a bunch of solids in that. It's taking its time. Oh, okay. This is kind of related. This is the concrete pieces that are in Villa Cecilia. This is like for one section. There's 10 of everything. Lower tie beam, I guess. Outer, lower rim. That's a tie beam. This is the upper tie beam. These two are tie beams into the center because it's a circle, and it naturally gets shorter. This is what we call spokes. That comes from the center circle to the outer circle. This sits over top of that. Outer post and inner post, the bases of the footers. This was done to figure out the materials list. Like there's 10 pieces that are 5.57 cubic yards. Cubic yard is smaller than a cubic meter by 10%, something like that. So it would be about 5 even cubic meters, if I'm guessing right. But you can add up all the cubic yards of you're building these houses out of cubic measures of masonry, cubic meters of concrete in the columns and tie bars, and cubic meters of material that's in your hollow blocks if you're using hollow blocks, or if you're doing slip forms, it's just like figuring the weight of a column. Okay, this is the shapes of the columns. What is this one? This is an outside column. The red things are the rebars going up. Those are the 16s, and some of them are 18s. Most of them are 16. 1, 2, 3, 4, 10, 12, 14, 16, 18, 20. There's 21 in this column, 21 vertical bars. And you notice that the bars have, the stirrups rather, wrap around the bars. Every place you got a vertical bar, it's restrained from moving out. Excuse me. It's restrained from moving out. Like this bar here is restrained two ways, so it can't move at all. Same thing here, we got a couple of things messing with that one. This would be this piece up here, but it needs flipped over to match the drawing. And this one needs flipped over to match the bottom one. And this one is a bar here. When you're doing a traditional rectangular beam, and you have if say we were just looking at this beam on the inside and didn't have all this other stuff, you see you have a bar here, and you might have two here and one there and two on this side. They're just laying beside a straight run of bar. It doesn't take much to move push that stirrup out. If this bar tries to buckle, it can't go in. It's restrained by concrete clear to the other side. But you've only got your concrete cover, 3 bar diameters on the outside of the stirrup. So if it's going to give, if you put enough pressure on it that it starts to buckle, it means bend to the side, put a bow in it, then it's going to bust right through there. So the proper way to do stirrups is you have a diamond shape stirrup. It goes around this, around that one, around this one, around this one, and back. And that keeps these mid-span things from buckling out. Rule of thumb is if these were 16s, the stirrups would be one size smaller, which here would be 12s. And if you were doing a diamond bar in there, it would probably be a 12, but if you're trying to save money, I'm pretty sure a 10 would work, because it's embedded so deep in all that concrete, and it's trying to push the concrete sideways clear to the corner, so that only time it's really under strain is right where it goes around the other bar. So you could do 16, 12, and 10, or you could do 16, 12, and 12. And they're just having too many sizes on site. This over here, the red things is part of our bending rig. They are